Okay, hi folks. I had a request to do a couple examples from 3A. So I'm just going to look at question 8 today because it highlights a problem in terms of getting a diagram in place, I think, and then actually how we can use moments in these questions. So this question here tells you there's a rod PQ. And so we know that it's hinged at P. So as soon as I hear that word hinged, I'm thinking, right, P's fixed, and I know there's going to be some kind of reaction force in these directions. What I don't know is if Q's over here, or vertically underneath, or to the side, so I need to keep reading. We know that Q has an elastic string on the other side of it, so I know that wherever my Q is going to be, there's another string. And then it tells me that the end of that string is attached to another fixed point R, which is on the same horizontal. So that means that there's another fixed point here, R, and that is on the same horizontal, and that must be 5 meters. So I carry on reading, and it tells me that the system is in equilibrium with PQR being 90. So actually Q must be down here with a right angle going in this direction. And then just filling in a bit of information. This was 3 meters, and it's uniform, so the centre of mass would be in the middle, so this is 1.5 meters, 1.5 meters, and the rod itself was 5 kilograms, so that's mass times G. Good. This is our string. I quite like to put a little curly line to remind myself that's the string. I also know that this angle here is theta. And I can see that my cos theta would be adjacent over hypotenuse would be 3 over 5. And then the force missing from the diagram here is definitely the tension. So this is a fixed point, so the string's being pulled up this way. So that is my tension. So then the question asked me to find the tension itself. So I definitely want to take moments at P, because that will just allow me to ignore my reaction forces. And so of the rod as well, I'm taking moments of the rod, that's why I don't need to think about any reaction forces at R, because they wouldn't affect the rod, which is just this bit. So if I'm taking moments at the point P in a clockwise direction, we can see the clockwise bit is actually this component of the 5G. Well, if that's theta, then this is theta. This angle is 90 minus theta, so this one again is theta. So we're going to end up with 5G cos theta, and then that's going to be equal to here's my lovely little L shape for my tension, so that is just going to be equal to 3 times by T. Cos theta was 3 over 5, so this is just 5G times 3 over 5 equals 3T. So lovely, stuff cancels, the 3's cancel, and I forgot to times this by the distance, whoopsie, so there should be a 1.5 in here as well, because that was just my component of the force. I forgot to times it by that distance. So I end up with 1.5 G is equal to my T, which tells me that tension is 14.7 newtons to 3 significant figures. Cool. So then it's just a case of thinking, okay, well, the natural length of the string. Well, this was a Pythagorean triplet, so we know that this here is going to be equal to 4 meters when it's extended. So that 4 meters is actually equal to my my natural length plus my extension. So if I wanted to keep everything in terms of my natural length, my extension is 4 minus L. So then I can use our classic favourite, T equals modulus elasticity times by the extension divided by the natural length. So I've got 14.7 is equal to, our modulus elasticity was given in the question as 30 newtons. So this is 30 times by my extension, which is 4 minus L, all over L, because L is what we are looking for. Multiply up, 14.7 equals 120 minus 30L. So 44.7 L equals 120, and then we just divide through, gives us an answer of 2.68 or 2.7 meters. Cool. So I think the key learning points from that question were really taking moments, because we've got that lovely L shape. When you take moments, it's of the rod. So we don't need to worry about the reaction forces here. It's just the forces affecting the rod. Taking moments at that point means we can ignore those reaction forces. And then because these lengths were given, we could actually find theta. And then, yeah, just using tension equals modulus elasticity times by extension divided by natural length. Hope that helps. Let me know if you've got any questions. Take care. Bye.